Welcome to the Rollup. Today's episode is with Jeremy from RiscZero, project that has built a general purpose zkVM based on the RISC-V algorithm. Now, before we get into the podcast, it's important that you have at least a basic understanding of ZK and ZKproofs. ZK stands for zero knowledge, and a zero knowledge proof is this innovation in mathematics that allows someone to prove that something is true without giving up any of the details about why it's true. You can think of this like, I can go to a bar, I can prove that I'm of age to drink at that bar, but I don't need to give away my actual birthday or any of the other information on my driver's license or ID. This is basically a ZK proof, and it has far-reaching applications to lots of instances in blockchain, as well as technology in general. And RiscZero has built this general purpose zero knowledge virtual machine to enable ZK proofs on several applications spanning Ethereum, as well as other blockchains that have traditionally not been able to get access to some of this software like Bitcoin. We're going to be talking all about RISC-V and RiscZero's general purpose zkVM in today's podcast. But before we do, here's a word from our sponsors that help make all of this possible. Enjoy. Navigating multiple blockchains can be complex and cumbersome. Let's say you want to deposit into a lending market on Polygon because they have the best rates, but you only have funds on Optimism. So you bridge your funds to Polygon only to realize that you need Matic to pay for gas. Maybe use a centralized exchange, or you ask a friend to pay for the gas, but only then can you finish your transaction. In a chain abstracted future powered by Connext, this is not the situation. You can connect your wallet to any dApp from any chain with all the complexities of swapping, bridging, and depositing, all completely abstracted behind the scenes. Head over to connext.network, that's connext.network, to learn more about Connext's chain abstraction toolkit.
Welcome back to the Rollup. Today we are talking about ZK with our friend Jeremy here from RiscZero. Really, we think ZK will eat modularity in a way. And that's been an article from these guys from Equilibrium and from Jebulot. And we are excited about ZK making a big entrance into the Modular Stack. RiscZero is working on zkVM, so we're going to dive into that, as well as some of the higher level concepts of ZK, and just talk about the implementation and kind of get a catch up as to where we are on the development of ZK and the practical use cases in today's world. Of course, here with Rob. Good morning, Rob. How you doing, man? GM, like it says on your shirt.
Yeah, it's another beautiful day in Florida out here, and excited to catch up on ZK because a little while ago we had done like a very general high-level overview of what ZK is. ZK, I mean, the space in general moves so fast that it's come a long way, and now we have like you said, modularity, ZK. We've kind of like here and there spotted and kind of like spotted progressions in ZK technology. And so RiscZero is coming out very, very soon with their like 1.0 zkVM, which we'll get into in a minute. I'm very excited for how that is going to push forward ZK in general. So Jeremy, welcome. It's a pleasure to have you on the Rollup, and very excited to learn more about ZK and especially the state of ZK as of recent from you and your stance at RiscZero.
Awesome, great. Thanks for having me. At RiscZero, we've been working on ZK quite a while, so excited to have a conversation about sort of where the state of things is and where it's going. So
Beautiful,
Awesome.
cool. So I think like we know ZK as like there's a couple things like don't trust, verify, and also like you can know something without having to know the contents of what this thing is, or you can know that something is legitimate without having to know what it is. There's a lot of terms thrown around like verifiable computation. Why don't we kind of start here? I know this is something that you guys champion at RiscZero. What does verifiable computation mean to you in the terms of crypto and in the lens of ZK?
yeah, absolutely. So I mean, I think one of the most powerful impacts of ZK has to do with the fact that it allows you to show that someone ran a computation correctly in a time that is much faster than the time it takes them to do the computation. So I can run a very complex computation, and then I can show I did it right And what's interesting is no matter how much computing I do, the amount of time it takes to verify it is always the same. And that's is really important for any sort of decentralization because it allows different people to work on different parts of the computation and then cross verify in a way that scales much differently, right? If you look at the sort of pre-ZK sort of blockchain approaches, the only way to tell whether someone did something right is to redo it yourself. And as a result, there's a massive amount of redundant computing that gets done, to verify the transactions on a given chain. With ZK, you can have some people working on some set of transactions, some other people working on some other set of transactions, and then you can just verify those, right? So I think the long-term impacts on scalability can't be overstated, in my opinion. And the other thing that is interesting is this sort of privacy property that you pointed out about ZK, which is that when I am doing that computation, I only have to reveal the parts of it that I want to reveal. I think that has a lot of use cases as well, but I think just the verifiable part of it is one of the more near-term impacts, right? Especially for things like L2s, et cetera.
When we think about RiscZero, and like you said, ZKproofs in general have kind of these two properties. They have the privacy property where we don't have to reveal all of the necessary components about like the state transitions or the transactions. We can just verify that they were computed correctly. That's kind of the privacy element. And then we have the succinctness property, which is that verification is much, much simpler to do than like actually doing the computation yourself. At RiscZero, do you guys focus on one of these properties or the other a little bit more? Or is it really kind of like both that you guys are trying? Like, what is the general mission of RiscZero, and how does it kind of pertain to each of these properties?
I mean, I would say that the general mission of RiscZero is to make the full power of ZK accessible to everyone, and not only in terms of the being able to run ZKproofs, but being able to develop ZKproofs, being able to encode the whatever rules you want, run whatever program you would like inside of a ZK system. And I think that most of these properties do become critically important. And so I think to some extent, it's hard to build a full system without all of the properties, right? Succinctness is absolutely critical for verification on blockchain. The verifiable nature of the computing is critical for almost all the use cases. There are some use cases that don't require the privacy aspect, but I think that there are enough that do that it's worth really trying to make that part of a product offering. I mean, I think that what our initial thesis, the sort of reason we started the company was this idea that in order to make a ZK proof, I mean, once I became aware of ZK technology, and I've been following it for about 6 years, it sort of blew my mind the fact that this is even possible, that it's possible to verify the correctness of a computation faster than it is to produce it. But I tried to convince a lot of my friends that ZK was the future, and when they asked me, how do you write a ZK program, I was like, well, you just implement some polynomial constraints over some finite field elements, and they're like, that's not programming, right? This is a very, very complex, difficult thing to do development in historically, right? When people were writing their own custom circuits, and you see these projects take months or years to get something done, even simple things, right? And so our fundamental thesis was, if you can make it so that people can write ordinary programs inside of a ZK system, that would sort of revolutionize the use of ZK. And so that sort of was our basic idea. And I think that there was concerns that people had that the performance of these general systems would be too slow, or that it wasn't possible to do this. And I think now that the whole industry with regard to ZK, much of it is moving toward this sort of general purpose, sort of direction. So I think that our hypothesis has been pretty well validated at this point. So we're very excited to get this stuff into production as well. So.
Yeah, definitely. There was a little bit of non-English in there for us who have little ZK understanding, but we're just going to bear with us on this pod, as we've done quite a bit of research, but there's still a little bit of what I call ZK magic language, which is a language that is exclusive for just a small subset of the world's population. So I applaud you for being a part of that population, sir.
Yeah, well, I think our goal is to make it so that to use ZK, one doesn't need to know any of these things, right? And I apologize if having built these systems, I unfortunately do sometimes speak a bit in code. But yeah, I think that I think a lot. I really believe that ZK is going to have a wide-ranging impact, both obviously in the entire blockchain industry, but I think beyond that as well. But I think that our goal as a company is to make the sort of technical complexity of ZK vanish, right? You think about public key cryptography and things like that. There was a time on the internet when communications between any two parties could be seen by everyone along the way, right? And no one wanted to, put their credit cards into a website because it just was being transmitted in clear. And then, there was all this work to build the PKI infrastructure and, the encryption infrastructure that we sort of take for granted today. And now the only difference between an unencrypted and an encrypted one is, HTTP versus HTTPS, right? It's basically invisible infrastructure. And, our goal is to make writing ZK so easy that it's just like, oh, do I want to run the program or in the ordinary, regular computing, or do I want to do it verifiably? And I'm just going to flip that switch, and then it takes me a little bit more effort to do the computing, but it's as easy as writing a normal program.
Yeah, part of what's being an entrepreneur is almost having a little bit of a crystal ball and trying to see the future in some capacity, right? You can't predict the whole future, but you can place your bets with your energy, time, and capital to kind of like see where the future kind of goes. And we had a podcast with Jem from Sovereign Labs, and he talked about their entire design being around taking a bet on not just there being just one zkVM or just effectively there being a lot of development in this space. And it kind of seems like you also had a similar hypothesis a couple years back as you were kind of talking us through that. So let's kind of talk about that evolution of these VMs and kind of how we got to where we are today. I think our audience would greatly appreciate kind of a chronological understanding of like how RiscZero came about today and kind of like this evolution of ZK to now, being a couple weeks out from RiscZero ZK VM 1.0.
Like I said, I had been following the sort of research for many years before this. But I think that we really started with this idea of making ZK more accessible. I think that we've seen in terms of the ZK development process and how people have done ZK, it going through a couple of different iterations. The first sort of generation of ZK was this sort of custom circuit idea, right, where you write a bunch of mathematical constraints that's supposed to represent your program. And we actually saw real applications using that sort of approach, right? Like sort of Zcash, and some of the very early ZK use cases did in fact make things that worked using that approach. And then you sort of see this sort of second generation, which is sort of in the Alio or some of the early Stark or Cairo stuff, where there's this idea of, well, we need to make this more accessible to programmers, so we're going to build sort of a custom programming language, so that it looks more like regular programming, but it's still very ZK specific. And I think that's it makes it much more accessible, but it's still you have to learn a custom language, and more importantly, you can't make use of any existing code, right? You want to maybe make a ZK thing that checks whether chess position is correct. Well, you have to rewrite the rules of chess yourself in the new language because there's no chess library because the language just came out, right? I think that people often underestimate the complexity of developer tooling and the power of a big ecosystem, right? So our question was, can we somehow make this, VM match the structure of an existing VM that people already use so that we can take advantage of all this existing code? And I think there was actually sort of two approaches, right? The sort of ZK EVM approach, where you try to build a VM that emulates the Ethereum virtual machine, so that you can use the Solidity code. And that's a very sort of lots of blockchain things that makes a lot of sense, right? But the EVM is a very complicated machine, right? And what we decided to do was take a slightly different approach at the time, which was quite novel then. And the idea was, well, what if we found like the most simple possible virtual machine that actually has software that already exists for it? And we settled on the RISC-V, which is a type of a processor chip, less common than Intel or ARM, but something that does have enough traction that the Rust compiler already supported that chip, and it's a very low complexity. And so our thought was we build a very low complexity, very high performance VM that can run arbitrary code, and then we use that to allow people to run normal code inside of ZK. And actually, what's interesting, what we found is that once we did that, we were able to actually make a ZK EVM by just taking the normal, like Reth, and the sort of the EVM components of existing Rust ecosystem, and just run those inside of our zkVM, and actually the performance, while not as quite as fast as something that's custom built for that EVM use case, we were able to do in weeks what other teams had been spending a year on, right? So I think that sort of shows to the power of the sort of general purpose nature and the reuse of existing code.
Beautiful.
Yeah. RISC-V chip here plays a pretty important role. I'm curious, because we haven't talked about this so much when we talk about ZKproofs. What is the relationship between the hardware component of one of these chips with kind of like the software component of what you're doing in that computing space?
Yeah, so we don't actually do anything with any specialized hardware, but the idea is that it's designed to look to the programmer, or to the compiler, right? Sort of like you're running on this particular chip, right? So we really are running just a virtual machine, but that virtual machine looks like a well-known, pre-existing, standard, well-defined piece of hardware. And by doing that, by making our VM match an existing specification, we get the power of being able to reuse all of the compiler work, all of the this work that's been done, that existed before we started. And so in some sense, that's part of the approach, right? And I think that it's similar in regards to the EVM approach, which reuses the well-defined nature of the EVM, although the EVM is changing much more rapidly, right? The other nice thing about RISC-V as a target is that it's a very well specified, and the specifications are very long lasting, and they change very slowly, because in the world of hardware, doing another rev of hardware is very expensive, and so you want these standards to be very stable, so that provides us with additional sort of, just makes things easier to do.
Cool. Interesting. Bear with us as we're just coming around to these ideas and just talking to you about our curiosities. And we were kind of talking about this idea prior to the recording, with regards to kind of like the commoditization of rollups, effectively or the commoditization of zkVMs, and then it's the knock-on effects of the complements of zkVMs, which is effectively rollups. And you're talking about how you can build generalized zkVMs rather than just custom circuits, which was kind of like the previous iteration of zkVMs. And we've kind of learned that this becomes possible by running a state transition function of a rollup in Rust through RiscZero. Now, there are a bit of like trade-offs here, if I'm understanding correctly, between a generalizable zkVM versus running like a full Rust, or a full circuit for your zk. Maybe we can talk about this commoditization of zkVMs, of the complements being rollups, and kind of like how you're thinking about the trade-offs between a zkVM versus like a more optimized full circuit machine.
Yeah, well, I think this is really interesting, because what it does is it makes it. I mean, I think historically, if you look at some of the early, pioneers that were working on specific use cases involving ZK, a huge amount of the value of those companies was in these sort of custom circuits. You're right, like, so there's like with like Zcash, for example, like there's a very complicated, a lot of huge amount of effort went into building the circuit, even though what it was doing was quite simple, mostly just sort of a Merkle tree lookup. And nowadays one can write very similar things using these sort of, generalized general purpose zkVMs much more quickly, like day, right, to do this type of thing. And in terms of people building rollups or L2s, it just opens up the possibilities so much, right? You don't have to hire a huge number of devs that are going to be focused on all these ZK details. You can just focus on sort of your application. And I think that not only will we see this lead to a lot more sort of zkL2s or other, things along those lines, but I also think there's this sort of emerging ZK coprocessing mechanism, right? Wherein you can move compute that's app-specific compute off-chain. So if you want to do, sort of a DeFi use case, right, where you're doing a big complicated order processing thing, rather than pay for the gas for doing all of that, you can do all of that compute in a general purpose zkVM and then just verify it on chain. And so I think as we sort of look forward to the future where it becomes very straightforward and inexpensive to verify these ZKproofs on chains, and very inexpensive to get them generated, right, as we bring down proving costs, you're going to see a lot of these things where you move significant portions of the computation off chain for scalability. And not only, will of course this lead to more sort of L2s, but I think there'll also be this other kind of like, L1.5, I don't know what you would want to call it, a sort of case where you have an application that maybe runs on the L1, but that does much of its computation off chain, but in a very app specific way, rather than having to, sort of move your liquidity into some L2. You keep all your liquidity on the L1, you just do your compute off of the L1, right? So I think that both those things are going to continue to become easier, and people who've spent a lot of time and energy building their ZK systems in the prior generation to do these types of things, a lot of that value is going to, be reduced as it becomes easier and easier to do these things more quickly.
Makes total sense. And then as a result of doing things, of building ZK in the current era with zkVMs, there's a bit more like flexibility and functionality in terms of being able to plug into like other SDKs and other kind of ecosystems of rollups, and kind of offer like a proving layer or a last or a fallback kind of mechanism. And again, referencing to Sovereign, because we talked quite a bit about RiscZero in that pod, we spoke about how rollups within Sovereign's ecosystem effectively are able to outsource proof verification to a kind of host of zkVMs. And there's some sort of like auction process in which these proofs are given to a winner, and then they are verified and kind of returned back to the rollups themselves. Let's talk more about some of these like practical applications of RiscZero zkVM as we get closer to the official launch of 1.0. Kind of what other practical expectations or applications are you kind of looking at, and implementations that you see or that you have lined up already?
Yeah, absolutely. We have a number of different partners that we are working with, both for sort of on the sort of L2 side as well as on the sort of more application specific side. And I think that you spoke earlier to this idea of making it easier to integrate with things. One of the other things that we've been working on is, within this sort of ecosystem, it's very easy to, for example, interact with Rust code, because Rust code compiles down to our zkVM. But it's also really important to be able to access like existing state that's on chain, right? So for example, running, we just recently put out a library called Steel, which basically allows the programmer to call EVM view calls and inside of the zkVM, so that they can run computations on the existing on-chain state. And so one of the cool things is, because we can sort of emulate the EVM just for a small section of computing, we can sort of allow the sort of way in which you can access on-chain state to be a lot easier. And I think that that's going to be highly valuable for a lot of these type of sort of applications. Yeah.
Okay, cool. And the other applicable use case that we've heard about is this idea of like a global state layer where you have all these different rollups and you kind of have to pull each individual state at a certain epoch and kind of bring it all into one global state layer. Perhaps this is more like an interoperability or like a proof
Mhm.
aggregation use case. But is this something that you
Yeah,
guys are thinking about as well?
absolutely. I mean, I think that there's actually one of the things that people, so the sort of immediate obvious use case of ZK is to sort of prove the correctness of a state transition. But what that means is that that also allows for sort of cross state messaging to be provably correct, right? So if you want to look at, moving, messaging across chains, or between rollups, for example, ZK allows you to prove these sort of state transitions on the far rollup to the one you're interested in sending a message to, and as a result, they mean that you can sort of have this interchain messaging happening, without having to wait for windows for optimistic delays or these kinds of things, right? So you can get a much faster, much more interaction between different sort of computing environments, different chains.
Fuel achieves higher throughput by utilizing a novel UTXO-based approach that allows for parallelized execution. This design significantly accelerates transaction processing, which enables Fuel to handle vastly more transactions than non-parallelized systems. Thanks to advancements introduced by Fuel, Ethereum rollups are set to be more powerful than ever before. And Fuel is not just enhancing Ethereum rollups, it's redefining them, making them faster, more scalable, and more adaptable to meet the needs of modern applications and developers. Go to fuel.network, that's fuel.network, to learn how to build on the Rollup OS.
So I think, and the second thing is really regarding sort of aggregation. And one of the really cool things about ZK, once you have recursion, which is an absolutely key critical feature for a modern ZK system, is that it allows you to prove two things and then prove that both those verify and then verify that resulting thing. So you're able to aggregate a large number of proofs into a single proof. And that is super critical for a number of reasons. One, it allows you to talk about a very large number of state transitions and verify them very quickly, even if the state transitions are being produced independently by different parties. So you can sort of have a lot more inter-party complicated sort of interactions, which I think we'll see a lot of moving forward. I think that's sort of, we're just sort of on the beginning of what that's all going to result in. And then I think the other really important part is just in terms of reducing the cost of things like verifications, right? So if you look at verifying these proofs on chain, to verify a single proof on chain by itself is on the order of sort of 300,000 gas, right? Which is quite expensive. Still cheaper than doing in some cases, if the computation is big enough, it's still cheaper to do it off chain and verify it. But if you look at how you can use aggregation, we're working on mechanisms that will allow you to have an amortized cost for verifying proofs that's more on the order of 20,000 gas for verifying a proof. And so the ability to do an arbitrarily large amount of compute off chain and then only pay 20K gas for it, I think is going to open up a lot of really interesting possibilities.
Yeah. As you kind of described that, it brought to mind this idea of like exponential succinctness.
Yes.
Because as a result of that recursion, you're able to save quite a bit of resources and preserve the succinctness property, actually apply that to multiple different, like, what would have been individual ZK proofs, but through aggregation, a single succinct proof.
Yeah, it's really crazy. Like, one of the amazing things about ZK is really you can verify effectively and arbitrarily large amount of computing with a single quick succinct check. And actually, in some ways, like Mina really sort of pioneered this in that their entire history of their blockchain is really verifiable by like a light client, right? And I think that this we will start to see the scalability. When you think about sort of wanting to scale the existing systems to an unbounded rate, right? We've seen a lot of work on people scaling the raw transaction throughput of a blockchain, but really the sort of long-term goal, in my opinion, of these decentralized systems is to make it so that as you add more nodes to the system, as you add more computing capacity, that the transaction rate scales up with the number of computers. Every additional computer you add gives you more transaction rate, gives you more throughput, right? And I think on the computing side, ZK already has all the necessary components to make that happen. And then I think on the data availability side, there's additional scaling challenges. But I think that that's, I think, largely solved at a theoretical level. I think that it'll still be a while before we see practical sort of truly horizontally scaling decentralized systems. But I think that the question of whether it is possible is no longer an open question in my mind, which I think even a year ago it was, right? So I'm really, really excited about what the future holds with that. So
it sounds so intuitive to think about that concept of add another computer, get more scalability. But when you take it on this verifiable and the verifiable nature of it, it means that all of these computers are going to have to verify the same thing. And so when you add another computer, it means that there's more redundancy. And so a lot of times we've seen that not like adding more nodes in the system actually slows down the scalability. Yes. It may add some security because it's another computer that is also doing the same computations, but because there's another computer that has to do the same computations, slows things down. The light node architecture just breaks this, and it means that we're actually able to kind of like divide and conquer a little bit. All of these nodes are able to verify the work of the other nodes, but because we have this succinct property, it means that they don't have to do we don't have to compute the exact same computations. We can just verify that those computations were correct, and then each of the nodes are able to kind of like specialize on their own little piece of that entire computation.
Yeah, and if you do it right and you roll the whole thing up from like a big tree sort of form, you can get it down so that all the correct execution of all the nodes on the system are all verifiable by a single very small thing that can be rebroadcast to everyone, right? So I think there's I think that long term, this is definitely the direction that things will move. And there's a lot of different ways to do it. Like there's an interesting question of whether it's a bunch of different sort of sovereign things that interact, whether it's a single giant, scalable thing that has the same execution model everywhere. I think there's a lot of opens, but I think that with the combination of ZK and some of the new things like data availability sampling and some of the other DA work that's been going on about making the scalable distribution of data happen as well, because that's obviously the other sort of part of it is the compute and the state. I think that I think these problems are very much soluble in the long term.
The ZK endgame, not only for interoperability, but for verifiability as well. When we get single slot finality, improved aggregation for cross-chain transactions, Jeremy will be in Mykonos partying and a big smile on his face.
Yeah. I mean, it's been the dream, right? Like, I think that, if you look at it, I think that there are so many applications for which, blockchain would be a great choice, but just is not technologically feasible to do right now, and largely this ends up coming down to costs, right? Like, I think that why not replace Twitter with like a truly decentralized blockchain version? Well, it really just comes down to no one's going to pay $5 of gas fees to click the like button, right? And I think that that cost, that $5 of gas fees, really comes from the sort of scaling limits which are induced by this, redundant computation, right? And so as you look forward to a world where we can actually really have this horizontal scaling, I think a huge wide range of new possibilities start to open up, right? So I'm very excited about where that's going.
zkVMs have been called like a funnel for prover networks.
Yes.
How does the RiscZero zkVM kind of work together with prover networks? And can you kind of just unbundle that and talk about kind of the interplay between these different components?
Yeah, because to be honest, guys, I thought zkVMs, sorry, Jeremy, I thought zkVMs were like alt VM thesis, like you've got like move VM and like SVM, Solana VM, but it's not really the same. is it? So
No, it's largely sort of, especially from our perspective, our VM is designed to be very sort of unopinionated and to allow you to run these other kinds of VMs inside of it, right? Because it's very much works like a normal ordinary processor in a normal ordinary computer. And so actually, we, for example, have some prototypes where we can actually run, the move VM, code inside of our VM. But and obviously we of course support running EVM things in our VM. So it's really sort of meant to be a lower level, more like a piece of hardware in that regard. But yeah, I think to go back to the sort of question about prover networks, I mean, I think that on the network side, we're starting to see the emergence of a number of different projects to do sort of prover networks to allow people who need zero knowledge proofs to be produced to be able to get someone with the right hardware to do the zero knowledge proof to do it. And I think that we're currently working on our own particular take on the sort of prover network as well right now, and we're sort of finalizing some of the design on that. But I think that it's the economics of it are still not, in my mind, fully worked out in terms of the sort of making sure that the supply and the demand match up. And I think there's also sort of an interesting separation on the marketplace. It's actually a little more complicated than just sort of a two-ended marketplace, because there's actually multiple parts to the process. In my mind, you could almost sort of separate this question of what I would call ZK settlement, which is the idea that I will pay X if I get a proof of Y, that the process of actually making sure that proof gets landed and verified where it needs to be verified for the use of the app, and the payment movement. That's sort of like settlement, from this question of matching, which is trying to figure out which person who needs a proof goes with which person who can produce the proof, versus any sort of also sort of reward mechanisms or ways of encouraging provers, or as well as all kinds of things like if you have a party like an L2 that wants to have ZK proofs produced reliably over an extended period of time, what they really want is actually like an SLA. And sort of how do you make a marketplace for things like SLAs? Is there a slashing mechanism, right? There's a number of these interesting things, because some use cases really want, I want to just pay for a proof right now and I'll pay whatever I need to pay. And some people want to know that the price is going to be stable for a while and that the proofs are going to get done, and that their L2 isn't going to grind to a halt because of a price spike in the prover market, right? So I actually think that the market mechanics, and also the other thing is that ZKPs aren't necessarily completely fungible, right? Like you might need a particular type of proof, or you might need a large proof versus a small proof, and different machines have different capacities for these things. So I think that the market mechanics of this are actually going to be quite interesting. And I actually think there's some value from a design perspective to separating out the questions of like the settlement part of it from the sort of matchmaking part of it, because I think there's room for a lot more innovation on the matchmaking side. The settlement process is really about how do you get the thing on the chain the most efficient way. So anyway, we're currently working on a number of these sort of problems. Currently the zkVM 1.0, if you want to run the verifier, you run it yourself. But I think, and if you want to generate a proof, you generate it yourself, or we have a Web 2 service Bonsai that you can use to do it. But I think that long term, there's going to be a lot of interesting things in terms of the status of prover market.
Cartesi is your home for app-specific rollups. At the forefront of developing new tools and platforms that enhance the capabilities of blockchain technology, Cartesi enables applications that are flexible and built to scale. Build on a full Linux environment and use traditional software libraries, but in blockchain development. Go to cartesi.io, that's cartesi.io, to learn more about building your own app chain today. The settlement part of like putting that proof on chain, that part in like facilitating the money movement and the payment for that proof, that's just another state transition. And
yeah, largely, right? Yeah, and I think that it's actually interesting because it really only requires you to know that the two parties agreed to the that there and that the proof matches whatever requirement that the client or user had. So I think that that's definitely uh, a can be looked at as a separate problem from the question of how do you figure out who's going to run what proof and how do you figure out the sort of price and sort of that whole market side of it. But anyway, I do think that there's a definitely we're just sort of seeing the beginnings of these kinds of things emerge, and I think that but I think that this is going to become increasingly important because um, there's obviously whenever there's a demand for something and there's a supply, making an effective market that works well for all the parties is a critical part of making the technology applicable.
Yep. This is all getting to the like the scalable nature of trying to bring down the proving cost enough so that someone who pushes the like button on Twitter doesn't have to pay $5 to press it.
I think the thing is that we've already passed the point where the cost of proving has gone down enough that it is now cheaper to prove many computations on chain than it is to pay the on-chain gas for that. But I actually think that there's been a lot of work on the sort of performance side from all the parties in this industry, and there's a lot of room for continued improvement. I think that we have in the last few months, the next release of our software is going to have some almost like 3x improvement in the prover performance. And I think that we still see a lot of fairly low-hanging fruit in terms of additional engineering work to bring the performance down even further. I think that we're actually getting very close. I sort of look at this question of I think we're only months away from being able to, for example, verify an entire Ethereum block, just using normal Rust, like REVM or whatever, for something like sub $1, right? And I think that as those cost numbers go down, the sort of things you can do just go up. There's certain applications that are cost limited, right? The Twitter like button being an example, but also just like there's this wide range of things, and right now ZK is applicable in cases where it's an important enough transaction, it's worth the extra cost. But as these performance things sort of continue to improve, we're going to see a much wider set of applications become economically sensible to do.
And what are the limitations? Like, I've asked this question before, and someone actually said that we're already operating at bare metal. So is it just a matter of adding more provers to the network, or adding more nodes to these prover networks, or what is the limitation, and how are we able to unleash that so that we do drive down these costs even further for zkProofs? And then ultimately unlock some new use cases.
Yeah, I would say that there has still been further sort of improvements in some of the underlying mathematics that underlie these things that can be taken advantage of. I think there is definitely lots of room for better code, just good old-fashioned engineering. We, for example, focus very heavily on doing really good GPU acceleration. But GPU acceleration is complicated, and there's room for us to improve there, and there's room for, I think, in general, the industry to really sort of just turn those numbers by just pushing on the engineering side. And then eventually you do get to the point where sort of the next logical step is sort of hardware for doing ZK proving. That's custom hardware, ASICs, and so on. I think there's a number of different companies working in that direction. We've been in discussions with a number of them to sort of make sure our proof systems are going to be able to use some of this hardware. All that said, I think there's still has been enough mathematical innovation that if you'd asked me a year ago whether it was really time to start building custom hardware, I'm like, well, you might end up discovering that the next innovation in proving systems renders your hardware obsolete, and hardware has a very long life cycle. But I think it is slowing down. But then I think the other issue is just giving the right incentive structure to make proving worthwhile. will just increase the level of supply. If there's really some actual money to be had by running ZKproofs, and that supply goes up, it'll provide more opportunities. So I think there's lots of ways that the cost will continue to go down. Where the bottom of that is, I don't know. Like we may be nearly done with new mathematical breakthroughs, but we might not be. It's very hard to see that future, right? So
Yeah. I think the kind of follow up for this main point of lowering costs to get more practical applications and to kind of get implementations happening is kind of introducing ZK into this modular stack that we have now. And I'm just curious from your perspective, where do you see ZK like eating modularity, or what parts of like the modular stack, if you think about, all the way from just the three layers of like execution and data availability consensus and settlement, but like extrapolate that to like sequencing and proving and RPCs and interoperability, and there's kind of list can go on as long as you want. I'm curious where you see ZK like really really making a big splash in the modular stack.
yeah, so I think in terms of execution, I think long term, nearly all execution is going to move to ZK, just because it does allow you to parallelize the execution. I think there's lots of places where DA and ZK fit well together. If you look at some of the latest work on like data availability sampling, they're using a lot of Reed-Solomon codes, which is a lot of the same sort of underlying mechanisms that are used in ZK. And there's sort of a number of different ways in which they interplay in that regard. I think in terms of interestingly, cross-chain interactions, the ability for ZK to allow you to verify something quickly is going to be highly critical. On the consensus side, I think the big value that ZK will potentially provide there, I think that one is more complicated. I think that there is some value for example, signature aggregation, or being able to sort of it depends upon what types of consensus mechanisms you use, though. So I think that's a more nuanced and hard to give a soundbite on. I think there's also a lot of interesting things where ZK will have an effect, sort of in terms of the ZK identity or interactions with sort of existing Web 2 stuff. For example, we've done some work in terms of using ZK to validate sort of your login to existing things like, Google or other things like that. So I think that there's going to be an interesting sort of the ability to take some facts from sort of the Web 2 world and make use of them in a trustless way that doesn't have any central parties or, involved. I think is another huge opportunity. So I actually think ZK is going to end up in a lot of different places, but the one that's I think most incontrovertible is the sort of execution side, where I think it will very much eat the world. So
Beautiful. Yeah, Jeremy, any closing thoughts from you about Steel and about kind of RiscZero V1.0 coming out, what our community can be looking forward to?
Yeah, I mean, I think we're very excited to help both the community in general and also our partners who are going to be launching with us, with the 1.0 or shortly after, to sort of be able to make use of this sort of power of the general purpose ZK. And I think with Steel, we're really looking to make that process very easier for Ethereum devs and to enable sort of these ZK coprocessor applications. We also, I just wanted to just send a shout out and a thanks for all the people who are involved in our trusted setup ceremony, which is going on, which is sort of one of the last phases of this process. And yeah, I think that's pretty much it.
Awesome, Jeremy. Thank you for coming on. It's been a pleasure to learn about ZK with you, and glad we spoke some English today.
I do what I can.
Thanks, Jeremy.